Now let's come to the next part. The last part concerned quantum computing, which is based on the principles of quantum mechanics, and especially I highlighted the superposition principle, because the superposition principle is responsible for quantum parallelism. And that is one of the essential advantages of a quantum computer. Now we come to quantum communication. And here in the center will be the other main principle of quantum mechanics, and that is entanglement. And here I like to start with this cartoon from the 80s of the last century. And perhaps you know, in communication, technical communication theory, it is usual to represent the sender of a message by Bob or Alice, and the receiver by Alice and Bob. Now, in the 80s, you remember the 80s were crucial with all these detection in the foundations of quantum mechanics. The first ideas came up of possible quantum computing and quantum communication. And this cartoon is relating to that. And you see, it is a cartoon exactly from that time. People are using these very old-fashioned phones. And now the idea, the sender is Bob and the receiver is Alice. And in the background of all this discussion, I remember in that time, was also the double meaning of Alice and Bob. Alice and Bob are fallen in love to one another. And this cartoon is a little bit playing with these semantics. Now, Bob is saying to Alice by phone, "Oh, Alice, you are the one for me." And the answer of Alice, the receiver, she is not speaking. Perhaps she is whispering, or she is thinking. That is indicated here by these points. But Bob, in a quantum world, how can we be sure? And that has, of course, a double meaning. The meaning of the everyday world is, oh my goodness, how can you be sure? Perhaps I have some other lovers also. But here in the technical context, the meaning is, how can our message be secure? And that is crucial, of course, nowadays in an age of cyber attacks. And now in the background, you see psi plus, psi minus. And these are mathematically the symbols of entangled states. These are the symbols of two examples of the so-called Bell states. And Bell states are formulas in the quantum formalism which indicate these entangled non-local situations which were discussed in the first part of my talk in a quantum mechanical context. And these are these four Bell states. That means corresponding to combinations of several classical bits here, 0, 0, 0, 1, 1, 0, 1, 1. Entangled states can be given by combined quantum bits. Here are the quantum gates. First quantum gate with the value 0, then with the value 0, and then corresponding to the classical situation with equal probability of all partial states. The point is that these four cases here, distinguished at first by Bell and proved by Bell, are entangled states. That means now you have already a physical imagination what entanglement means. Remember the bodies or particles at different positions and locations in the Einstein interpretation, independent from one another, but in the quantum interpretation, non-local in a common state. And mathematically, that means, and that must now be believed by you, mathematically, that means that this expression here cannot be separated, factorized in two terms independently from one another. Mathematically, that is expressed by a so-called tensor product. That is mathematically not possible. But what does that mean? Psi minus, for example. Both qubits have opposite settings here. Observation of qubit 1, that is here, with value 0, leads immediately to the observation of qubit 2 with value 1 and vice versa, immediately. And that is expressed here in this expression, which again cannot be factorized. Please think of the physical situation of the isolated bodies or particles, which here are not possible. That is a common state for these different bodies. Now, it seems to look a little bit technical, but I promise you, you will understand the following situation here only on the background, on the mathematical details which were already introduced. The problem is the following. Entanglement, and that was the shocking message for Einstein, seems to be spooky in the sense that entanglement seems to promise that immediate exchange, spontaneous exchange of signals, of messages is possible if you can realize an entangled situation. And that is now made precise here in the following situation. That is Alice. Alice is the sender of the message and Bob is the receiver. And Alice has a quantum bit, X, the input here, in a certain state, that is psi. We know already this state vector, alpha 0 plus beta 1. And she likes to send this message to Bob. That is the task. Now, the idea is to realize that by entanglement. We must entangle the sender with the receiver, Alice with Bob. And that is done here in the sense of the EPR experiment. That means we have a common source, and the idea is that Alice has a quantum bit, A, at her disposal, and Bob has a quantum bit, B, at his disposal. And now the idea is that both quantum bits are entangled. That means they are represented by one of these Bell states which I introduced before. That is this expression, and perhaps you remember that is exactly phi prime here, this expression here. And that is the task now. And now that must be realized by a quantum circuit. We need a machinery, a quantum computer, to realize this kind of quantum communication. Now the first task is to realize this entanglement, the entanglement of the two quantum bits which are used by the sender and the receiver. And that is illustrated here in the circuit, in the diagram. Here you recognize these symbols of the quantum gates, and I will explain them step by step. Now at first the entanglement. The entanglement is realized here. These are the two inputs for the bits of Alice and Bob. Now in the first channel, we at first apply the Hadamard operator. And here in that channel, nothing happens. That means, mathematically speaking, here is an identical operator. And if you like, you can imagine these operators are represented by matrices. And now we apply the C0 operator. That is indicated here, H and the combination with the identity operator to 0, 0, and now our C0 operator. And you remember my remark, and that is now proven here. The application of this quantum gate delivers an entangled state, namely one of Bell state, that is C+, and that can done here. If I had time, we could do it together step by step. It's a little bit boring with applying all these well-known calculation rules of calculating with matrices. In the end, it is simple school math or beginning of mathematics. That means the result is exactly this expression here. That is the situation. Now we have the entanglement mathematically represented. The task is that Alice wants to send the message psi to Bob. That is that channel. That means the task is now to use the entanglement here, that is here. We have now the mathematical representation. For that, combine it with our message psi. And that is mathematically represented here. Again, now to the combination of psi and Bell state, representing the entanglement. Here is the application of the quantum gate C0, entanglement. And that is realized here in that step. And we can calculate the corresponding expression step by step. No great problem. But then in this channel, we applied the Hadamard operator. That is indicated here. Hadamard operator applied to here the entanglement of these two values. And if we calculate this application, it's a longer application, but don't worry, simple calculation rules, nothing exciting. But then in the end, we get this expression here. And that is the expression that is illustrated here. That is the expression which is sent to Bob. That means Bob has in the end, by entanglement here, has this message here. And this message is amazing because have a look on it. It consists of 4 parts. 4 parts. And here we recognize the message which should be sent. And here are other cases of possible messages. And these are connected, let me say, with a certain key. And there are 4 parts. That means the keys are 0, 0, 0, 1, 1, 0, and 1, 1. And they are combined with the corresponding messages. That means for Bob, he has already this information. But in order to get the target information of Alice, and that is here, he needs to get an information of the key. And that is realized here by a classical challenge. That is no entanglement. That is a classical channel, maybe smartphone, and saying how. Now the key is 0, 0. And that can be observed by anyone because all the other people don't know what Bob already knows, because he, by entanglement, got this information. So Bob get the key by Alice, by a classical channel 00, and then all is fine. He has this message. He can select this message. Now, if we like to send this message here with the exchange of alpha and beta, then Alice sent the key 01. But what does that mean? Because C is here the input of her. She has to change the message. And that is realized here, the change of alpha and beta by another gate, quantum gate, that was the X gate, the bit flip. But if she wanted to send this message here, that is alpha, beta, but now beta with a minus sign, then that needs a manipulation by another quantum gate, and that is the so-called Z quantum gate that exactly realizes here the change of the sign, the so-called phase flip. Now, in this case, not only the components are exchanged, but also the sign is changed for the second term. And that is in the end a combination of X and that. And that is here realized in this circuit. So in the end, in this simplified arrangement, it is shown what can be done by quantum teleportation of information. The point is, of course, that the spooky situation which horrified Einstein is technically exactly not realizable. It is not sufficient. That is the precise message here. It is not sufficient only to use entanglement. You need some classical challenge. But the positive answer is this teleportation, quantum teleportation, is in the end absolute cure, because this is immediately, Bob gets this terms here immediately. But of course, it needs this additional information here. And the other good information is here that this teleportation by entanglement is absolutely secure, because it is immediately, exactly in this point. That means nobody can hack here and can observe what is going on, because there is no time. It is immediately got by Bob. And that is an example to make in a precise sense for you on an elementary base the situation of quantum communication with its restrictions, but also with its advantages. And that is nowadays used in technology. And it was at first applied here in Europe by the research group of Anton Zeilinger in Vienna. And he realized that for far distant communication in Austria, in Italy especially, and between different cities. And some of his students were Chinese students, PhD students. And they later on became very influential in China. So China is now the leading nation concerning quantum communication. And they nowadays try to realize that by satellite technology, that is illustrated here. That means the idea that far distant stations, for example, Beijing and Shanghai, are prepared in an entangled situation. And that is done by satellites. The satellite is sending a beam here with photons, of course, the dotted line, to the one Earth station and then to a far distant other station. And then you can arrange technically the entangled situation of both photonic beams. And so you have this common source that is nothing else than the EPR experiment, which is used now for this kind of immediate communication. And of course, it has nowadays a lot of technical problems because it must be related to the distance of the satellites and the number of the satellites, which are needed in order to realize what we can call a quantum internet. And I think, personally, that is the future. And this kind of quantum internet, that's also my personal idea, will not only be restricted to a quantum internet at our Earth. It will be used in space exploration. Because, you know, with our spaceships in the future, we have the great problem of the immensely large distances between the Mars and the Earth and other planets in the future. And that is a problem our communication will suffer. And of course, the security of these message transfer. And that in the end will be realized. That's my personal, is of course a technical vision for the future, but it is physically possible. With this projection in the future, I will stop here this part and thank you for your attention.